Unprecedented scale and complexity. SpaceX's Starship represents the most ambitious and complex rocket system ever developed. Its sheer size, standing over 120 meters tall, and the innovative design push the boundaries of current aerospace technology. This scale and complexity introduce myriad challenges, especially during critical phases like reentry. Reentry dynamics. The process of reentry into Earth's atmosphere is fraught with extreme conditions, including high velocity, intense heat, and dynamic pressures. Starship's upper stage, designed to withstand these conditions, faced unforeseen issues that compromised its structural integrity. Heat shield performance. A pivotal factor in the reentry failure was the performance of the heat shield. Designed to protect the spacecraft from the searing temperatures of reentry, it may have experienced unforeseen failures or inefficiencies, leading to critical damage. Aerodynamic instability. The upper stage's aerodynamic stability is crucial during reentry. Any deviation in its intended flight path or attitude can result in excessive thermal and mechanical loads, potentially leading to structural failure. Engine relight challenges. For a successful reentry and landing, the spacecraft's engines need to reignite precisely at the right moment. Any failure or delay in this process can lead to an inability to slow down and control the descent, contributing to the reentry failure. Material limitations. The materials used in the construction of the spacecraft must endure the harsh conditions of reentry. The failure could be attributed to the limitations of current materials or their application, which may not have performed as expected under real-world conditions. Flight software and control systems. The spacecraft's flight software and control systems play a critical role in navigating the reentry phase. Any glitches, inaccuracies, or failures within these systems can lead to a catastrophic failure by mismanaging the spacecraft's orientation, speed, and descent. Testing and validation procedures. Although extensive, SpaceX's testing and validation procedures for the Starship may not have fully captured the complex realities of reentry. This discrepancy between test conditions and actual reentry conditions can lead to unexpected outcomes. Operational experience and data analysis. Every launch and reentry provide valuable data and experience. This third launch's failure underscores the gaps in operational experience and data analysis that SpaceX continuously aims to fill as part of its iterative development process. Ambition versus reality. Finally, the ambitious goals set by SpaceX with Starship push the limits of current aerospace engineering and operational capabilities. While striving for revolutionary advancements, the path is fraught with challenges and setbacks, as demonstrated by the reentry failure. Unprecedented atmospheric phenomena. During its third launch, the SpaceX rocket may have encountered rare atmospheric conditions not previously modeled or anticipated, such as highly turbulent wind layers or unexpected electromagnetic disturbances, which could have thrown off its trajectory or interfered with onboard electronics. Material fatigue underestimated. The iterative reuse strategy of SpaceX emphasizes the importance of reusability, but the cumulative stress and microscopic material degradation from multiple launches and re-entries might have been underestimated, leading to critical failure on the third launch. Advanced cyber interference. Considering the high-profile nature of space missions, an advanced cyber interference effort by malicious entities could have targeted the rocket's communication or navigation systems, subtly altering its course or functionality without immediate detection. Quantum compass interference. The use of cutting-edge quantum technology for navigation could be susceptible to interference from cosmic rays or solar storms, phenomena which might have been stronger or more disruptive than calculations predicted, leading to navigational errors. AI autonomy anomalies. If SpaceX employed advanced AI for real-time decision-making, an unexpected anomaly in AI behavior, possibly due to an unforeseen loop or data interpretation error, could have led to miscalculations or inappropriate adjustments during critical re-entry phases. exotic particle interaction. The rocket might have passed through a region of space with high concentrations of exotic particles or dark matter, which are not fully understood and could have unpredictable effects on physical systems, including propulsion or structural integrity. Thermal protection system overlook. Innovations in thermal protection might not have accounted for the specific conditions encountered during the third launch's re-entry phase, leading to overheating in critical components not previously identified as vulnerabilities. Interstellar dust accumulation. Accumulation of interstellar dust on sensors or critical surfaces could subtly alter the rocket's mass distribution or interfere with sensor accuracy, leading to miscalculations in thrust or trajectory adjustments. Harmonic resonance cascade. The rocket structure could have hit an unanticipated harmonic resonance frequency during launch or re-entry, amplified by the specific conditions of this third launch, causing cascading failures in structural integrity or system functionality. Undetected manufacturing flaws. Despite rigorous inspection and testing protocols, a subtle manufacturing flaw in a critical component, perhaps introduced by new materials or production methods, may have gone undetected until the unique stresses of the third launch exacerbated it into a critical failure. SpaceX's Starship's re-entry failure during its third launch is a stark reminder of the formidable challenges inherent in pushing the boundaries of space exploration. This event underscores not just the technical complexities but also the audacious nature of SpaceX's mission to revolutionize access to space. The re-entry phase, a critical juncture in any space mission, is fraught with extreme conditions, searing temperatures, dynamic pressures, and high velocities that test the limits of engineering and material science. The failure of the Starship's upper stage to survive this phase can be attributed to a constellation of factors, each highlighting the monumental task at hand. The design and scale of the Starship, ambitious and unparalleled, bring to light the intricacies of managing heat, velocity, and structural integrity during re-entry. The heat shield, a critical component designed to safeguard the spacecraft against the inferno of re-entry, might have encountered unforeseen inefficiencies or failures. Such a scenario suggests a possible gap in our current understanding or application of thermal protection systems. Moreover, maintaining aerodynamic stability during this tumultuous phase is paramount. Any deviation from the intended trajectory or orientation could exponentially increase the thermal and mechanical stresses on the spacecraft, leading to catastrophic outcomes. The challenge of reigniting the spacecraft's engines for a controlled descent further complicates the re-entry process. This step is crucial for slowing down the spacecraft and ensuring a precise landing. Any misstep or malfunction in this phase can derail the entire re-entry maneuver, underscoring the importance of reliability in the spacecraft's propulsion systems. Materials science plays a pivotal role in the construction of a spacecraft capable of withstanding re-entry conditions. The limitations of current materials, or perhaps their application, might have been laid bare during this failed re-entry attempt. This incident highlights the continuous need for innovation in materials science to meet the extreme demands of space travel. Flight software and control systems, the brains behind the spacecraft's operation, must perform flawlessly to navigate the spacecraft through the gauntlet of re-entry. Any flaws, inaccuracies, or failures within these systems can lead to a failure to manage the spacecraft's orientation, speed, and descent effectively. The testing and validation procedures, although extensive, may not fully replicate the harsh realities of space. This gap between simulated tests and actual conditions can lead to unexpected challenges during missions, as seen in this failed re-entry attempt. Such outcomes emphasize the need for a rigorous and iterative testing process that closely mimics the conditions of space. Moreover, each launch and re-entry attempt provides invaluable data and experience. This iterative process of development, testing, failing, and learning is fundamental to advancing space technology. The failure of the Starship's third launch re-entry serves as a potent learning experience, contributing to the collective knowledge and expertise required to overcome the hurdles of space exploration. Finally, SpaceX's ambition to redefine space travel with the Starship is a testament to the human spirit's drive to explore, innovate, and push beyond known limits. This ambition, while laudable, comes with its set of challenges and setbacks. The reentry failure is a humbling reminder of the gap between ambition and reality, necessitating a steadfast commitment to innovation, perseverance, and learning. In conclusion, the journey to perfecting space travel is a marathon, not a sprint. It is a path marked by setbacks, learning, and gradual improvements. The failed re-entry of SpaceX's Starship is a pivotal moment in this journey, offering crucial insights and lessons that will undoubtedly contribute to future successes. As we look forward to the next steps in space exploration, we do so with the knowledge that each failure brings us one step closer to our ultimate goals of exploration and discovery. Remember to subscribe to the channel and leave a like on the video so you don't miss the next updates.